Cool. Yeah, cool. We can get started. So to start with, we would like to think of a scenario where you have built an application and it's maybe your pet project or maybe it's a client's application, and you decide to deploy it, and after a lot of work you decide to take a hard night rest, and before taking a rest you put your application on social media because you think it tries to solve a problem that you really care about, and what happens the next day is probably something like this. You couldn't anticipate the traffic that you got, and you had to manually go up and fix the application, maybe give it some more resources. In this case, the client suffers. This was a case that was happening in our project as well. We would get late night calls at 12 p.m. saying there is lag on Kafka, go and manually scale the pods to keep up with the lag. And this is not a good situation to be in. Well, to start with, let's discuss what does scaling even mean before going into autoscaling. So scaling here just means adjusting the capacity based on the demand of the workflow. That means if the demand is going up, you scale the capacity upwards. If it's going down, you scale it downwards. Before autoscaling, this used to be an estimate. This used to be a guess. Before there are holidays, before there are some major events, you would guess, the customers would probably use my application, so I would manually go and scale up or scale down the resources. But this is often error prone because what would end up happening is either you would over provision, in which case you would have more capacity, you would anticipate more customers, but then you are paying for hardware that is that you have provisioned, in which case you are paying for the cost. The other case is under provisioning, where you couldn't anticipate the growth in customers and your hardware couldn't scale for that. If you have ever used an application for maybe getting the results of an examination, on the day the results are announced, the application probably doesn't scale to the number of requests. This is a classic case of under provisioning. And to solve this, we use autoscaling, in which we can use two types, which is first is horizontal based autoscaling, where you scale outwards, and the second is vertical, where you scale upwards. Kubernetes itself supports three types of autoscalers. The first one is node autoscaling, and for this there are two tools that are widely used. The first is Cluster Autoscaler. This is a very popular tool. It is backed by the Kubernetes SIG. These are special interest groups who contribute to the source code of Kubernetes. So the Kubernetes SIG for autoscaling have built this Cluster Autoscaler, and it basically increases the number of worker nodes in your cluster. Another very popular tool is Carpenter. This initially started as a tool for specifically to AWS, and it gave you fine-grained control to scale the number of nodes. And since then, it has branched out to more cloud providers. This is the first type of autoscaling. The second is pod autoscaling. This will change the number of pods or even the resources of the pod. If you change the resources, it is called as Vertical Pod Autoscaler, or VPA for short. And if you change the number of pod itself for your application, it is called as Horizontal Pod Autoscaler, or HPA. And lastly, if you want to scale based on some events, you would use a tool called as KEDA. We'll cover all of this, what all of this means soon. So yeah.
Yeah, so before looking at each of these autoscalers, let's set the stage, understand few of the core components that work in KTest that will help us in understanding these autoscalers better. So yeah, let's start off with the pod. So most of you, I would believe, would know about it, but let's just quickly cover. So a pod is basically the smallest deployable unit in KTest. We containerize our app and then we kind of wrap it with the pod, right? So a pod can contain a single container or more than one. Generally, we run only one container, but there's the concept of side containers where you might run more than one containers as well. So our applications would want to talk to each other, and that's where we need some connectivity, and that's why we need a IP address, right? So the pods can communicate to each other. So in KTS, each pod will have a unique IP address. Along with that, some of our applications would need some would want to store some state, and for that we would need a volume mounted on it, right? So this is kind of similar to what we would have worked with, like Docker, right? You would want to mount a volume. A Docker container will have also some IP address. We are just extending that concept to KTS, right? Yeah. So the next component is nodes. So in KTS there are two types of nodes, but it doesn't matter which type of node it is. You would be always running some kind of pods on it, right? But what this distinction is, there are like worker nodes and there are control plane nodes. So worker nodes basically run your application, or the pods on worker nodes are your applications. Whereas there's the concept of a control plane in KTS, which basically means a bunch of nodes that only take care of managing the cluster, right? So these nodes don't run your application. These runs other pods that are just for managing the cluster, right? But no matter what node it is, you would be running some kind of pods on those, right? So extending, since our nodes are running pods, we would want to extend the concept of connectivity, network connectivity here as well. So a node should be able to connect to each other, as well as since we are attaching volumes to our pod, we would want to attach disk as well to our nodes, right? So another key thing here is what makes a node, right? Because a node can be a simple EC2 machine, it can be a VM, right? So it's the kubelet which kind of registers that node as part of the cluster, right? So that the pods can get scheduled onto the nodes. Along with this responsibility, the kubelet also handles like how pods are running. It manages the pods. Let's say you want to kill a pod, right? Who does that? The kubelet would have to do that. Let's say you want to create a new pod, right? Kubelet will have to deal with that. So the kubelet is kind of the controller of, or like the representative of the cluster onto a node, right? Yeah. So the next thing is, suppose you try to create a pod. So while creating a pod, you would give some requirement. This can be like what CPU and memory I want to be created, what image I want to use, what volume I might want to attach, right? So you apply this. You apply this. You might be applying this through kubectl, or you might be applying it through some kind of Helm release model, right? So in all of these cases, you are basically trying to create a pod, right? So how does a pod get scheduled or run onto a node, right? So that's where the scheduler comes in. It takes in the request for a pod. Now a scheduler sees a bunch of nodes, right? So it has to decide which node a pod should get scheduled on, right? So it has to basically come up with one single node which will run our pod. So it does it using two steps. First, it filters the node, and the second step is the scoring of the nodes. So talking about the first step, basically it will filter the node. So this filtering would depend on what, let's say, which node has more more amount of bandwidth remaining, because you would want to load balance or balance all the pods across the nodes. It would also look at if you have taints and tolerations in place. I won't go into taints and toleration, but you can read about it. It is basically saying you don't want some pod to be scheduled on some node, because you might have some, you only want that node to be you want only that node to run only specific kind of pods, right? So in that case, you would want to filter the nodes as well. Now after filtering these nodes, it has to score them or rank them, right? So ranking is basically weight basis, where it will rank based on different criteria. It will come up with the rank of it, and it will choose the node with the highest rank. Now what criteria these can be? Like these can be like again the same utilization. It can be a topology. It can be again taints and toleration. So all of these things it would again look at it and rank them. Now after ranking them, it will basically pick the node which has the highest rank. Now it can happen that you have two nodes with the same rank. In that case, it doesn't have anything else to look at, so it will pick any of those nodes randomly. So after picking a node, it will send a bind request to the API server, right? So you can think of like API server as the brains of KTest. So it will send a bind request saying schedule this pod onto this specific node, right? So once the API server gets it, the kubelet keeps on asking the API server, do I have anything pending request that I want to take up? So the kubelet will see, hey, I have a pending request, I need to take it up and act on it. So it will get that information of the new pod and it will schedule it onto the node. Yeah, so this is what your scheduler feels on a everyday basis. It is that sweaty gamer which is trying to min-max everything. Yeah, now let's look at another core component which on which of the it filters and ranks them, right? So nodes are registered onto the cluster, right? So it has that information that how many nodes, worker nodes I have. Then it will pick that information, and then it will have the details of each of these nodes, right? What's the current utilization? What's the kind of pods that are running? And then it will act on it. I think they decided. Now I'm not sure whether you can set it yourself, like different weights. But yeah, it has some internal logic which it uses. Yeah. 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 So it's a slightly longer talk. We will be. Can we just offload it at the end? That way, like we can answer it better, and it won't take that much time here as well. Yeah, so now let's look at the next component, which is the metric server. So all the like most of the autoscalers would heavily use this information because it's just plain getting the metric, right? So before acting on before scaling up or scaling down, you would want the information on how to do that, right? Now each autoscaler will use this information differently, but yeah, here that would get exposed. So okay, let's look at this diagram from right to left. So we already know about kubelet. A kubelet is a process that is running on our node. So a kubelet has a sub process called cAdvisor, which basically gathers the container information. So container metric information, it gathers those, and then it gets exposed to the metric server. Now metric server internally exposes or sends it to the API server through something called metrics API. You can read about it more, but it's like a simple API only. Yeah, after it is exposed, all the autoscalers can now gather this, get this information and start working on it. You can even try this out yourself. If you have a metric server as part of your cluster, you can run this kubectl top command, which will basically you can use to get the metric of a node or a container as well.
Cool. Now that we have looked at a few basic concepts of Kubernetes, let's look at the first type of autoscaler, which is node autoscaling. And even going forward with what node autoscaling does, let's see why you would need it in the first place. So yeah, for explaining this, we'll look at a problem. This is a very famous problem. It's called as the bin packing problem. It goes something like this. You have a collection of bins. Each bin has some capacity. So here we have 3 bins of capacity 10, 20 and 15. And you have some items. Each item also has some size. And the goal is to put the items within the bin such that no bin exceeds its capacity and the number of bins are minimum. This is a very famous problem, but What is an edge case of that problem is, what if the bins are full? Then where would you place any new item that comes? Well, in this analogy, the bins are your nodes in Kubernetes. The items are your pods. They have some request of, I need some amount of CPU or memory. And your scheduler is trying to take the item and put them into existing bins. And if the bins are full, you simply add a new bin. This is what node autoscaler does. Once the capacity for your nodes is full, it adds new empty bins to put items within. So let's take a look at how a scale up would happen if we were to use Cluster Autoscaler. Whenever you schedule a pod, as Amit mentioned, there is a sweaty gamer in your Kubernetes cluster. He's trying to put that pod into existing bins. But if the bins are full, you have Cluster Autoscaler. Now Cluster Autoscaler keeps track of the resources in your cluster. It does so by using the watch API of kubectl. You can also register to the watch API and build your own cluster state. So this is what it does. It keeps on maintaining the state of the cluster. And whenever it sees a pod that is pending, a pending pod means it's not yet scheduled on a node. Whenever that pod has a status of unschedulable, the scheduler sets status on pods, and if it's unschedulable and pending, Cluster Autoscaler keeps track of such pod, and it runs something called as simulations. So as we can see, it has its own cluster state, and Cluster Autoscaler is specific to cloud providers. Now each cloud provider has a concept of a node group. These are just collection of nodes with maybe some same instance type or some other way to group them. For example, in AWS, you have autoscaling groups, which are a collection of nodes. Similarly, if you are using GCP, you must be familiar with instance groups. These are again collection of nodes. So your Cluster Autoscaler runs simulations where for each of the node group for your cloud provider, it will simulate adding that node into the cluster, adding a new node in that node group, and then seeing whether or not that pod is scheduled on that node. So it also has its own scheduler, its own sweaty gamer running in memory. So once the simulations are done, you will have a collection of node groups that can be added. A new node can be added onto those node groups. After that, it runs something called as expander. This is configurable. So if you have a collection of node groups, how do you know which node group should I add a new node to? Well, this is configurable. The simplest one is random. You tell it from a collection of node group, choose any one. There is also least waste, where you would add a node which has the minimum capacity to accommodate this pod. So based on this, your Cluster Autoscaler, it runs some simulation. Based on the expander, it selects a particular node group, and then it sends a request to your cloud provider saying, for this particular node group, increase the number of nodes by 1. So in case of AWS, for example, it will tell for a particular autoscaling group, increase the desired nodes by 1 more to accommodate this pod. And the end result is that you have a collection of nodes and a new node where this pod that was pending can be scheduled. So you have essentially bought an empty bin, and this item can be put into that bin. This is the scale up cycle of Cluster Autoscaler. Similarly, when the load decreases, when pods are no longer being requested, it also scales down. It does so by identifying unneeded nodes. Now, unneeded nodes are nodes which meet 3 criteria. The first one is that the node is underutilized, meaning the resource utilization on that node, it's less than 50%. This is again a configurable value. So that's the first criteria. The second criteria is scale down is currently not disabled. So scale down can be disabled by setting a flag in Cluster Autoscaler. So this is the second criteria. The third criteria is that the pods on that node, they can be removed and scheduled onto other nodes in the cluster. That means the items within that node, they can be taken out and put into existing bins on that node, on that cluster. So then again, it does the same cycle where it runs simulations. It tries to remove the pod from that node in memory and then see whether or not the pods on that node can be scheduled onto other nodes. And if it finds a node that is unneeded, that means it satisfies these 3 criteria for more than 10 minutes, it considers that node as to be able to terminate it. So it sends 2 commands to this node. The first command is called in and the second is drain. Now called in is a command, you can also issue it to your nodes in the cluster. These 2 commands are usually used for maintenance on your nodes. So the first command called in, it tells the kube scheduler that this node is called in, you can't schedule any new pod onto this node. And the second command is drain, it tells the kubelet that is running in that node to evict all of the pods on that node. And then the scheduler again sees new pods and tries to put those pods onto existing nodes. So the end result is that this node it is no longer schedulable, and no new pod can be scheduled on it, and there are no pods running on it. And after there are no more pods running on that node, the Cluster Autoscaler, it uses your cloud provider's API to again decrease the remove that node from your cluster. So it sends a terminate node request to your cloud provider, and the end result is that you have one less node in your entire cluster. Well, the reality is that this entire process of seeing a pending pod, maintaining a cluster state, running simulations, telling your cloud provider to add or remove a node, it takes too long, it takes a lot of time, and within that time the pod will still be unschedulable. So you might see potential downtime where that pod is not actually running. And to solve this, we use something called as over provisioning, which is basically, if you have a set of nodes in your cluster, you would have one node which is empty, it has a pod that does nothing, and this pod in Kubernetes you can give priority classes to pods. You can say that in this bin which is empty, schedule a pod which does nothing and which has a lower priority than other pods. And this is basically called as over provisioning or having warm nodes. And what the scheduler does is it considers this priority while scheduling the pods. So if it finds a pod, a new pod that needs to be scheduled, it looks at pods that can be evicted from other nodes. So if we have a pod that has a lesser priority, it will evict that pod and it will schedule your important application pods onto that node. So this is a concept that is followed usually when running Cluster Autoscaler. Yeah.
Yeah, so next we will be looking at vertical pod autoscaling. Before understanding what vertical here means, let's first understand what is the need or where can be helpful. So suppose you are running a stateful application, right? So by stateful application here, I mean like some sort of service where you want identity and state attached to it, right? State meaning you are storing some things and you want the same pod to get the same state that it had, right? So in that case, it can be your simple Prometheus server, it can be your Zookeeper server, or you might be one of those brave folks who run Postgres. So it can be even that, right? So so people who would have worked with some of these things would already know that scaling them horizontally or scaling them is a challenge, right? So you have to keep on increasing CPU and memory as and when you hit the limit, right? So taking the example of Prometheus, so if you don't have a federated setup, by federated here I mean kind of basically a cluster setup, the only thing you can do is scale up your Prometheus server by increasing the CPU and memory, right? So this is the first problem of under provisioning, where you are constantly hitting the limit of the current resources that you have set. The second problem is suppose you don't want to deal with this problem. What you do is, like in general, is you give it too much, right? So you don't have to touch it for a long time, right? But in that case, you are wasting a lot of resources and you are paying for that even, right? So we don't kind of optimize it, right? We don't look at it. We don't want to deal with it. So we give it as much as we think it would need in the future, right? So this is the problem of over provisioning, right? Now, suppose we have a tool which can look at the usage, both historical and current, and come up with a more accurate metric, more accurate resource that should be set, right? So that is the job that VPA does. So yeah, let's look at the VPA's architecture. It has 3 core components. The first one is the recommender. So recommender's job is basically to look at the current metric, look at the current usage, look at the historical averages of the containers, and come up with the recommendation that suits it, right? We will be looking at how these are calculated in the upcoming slide. The next component is updater. So suppose recommender's job is just to come up with the recommendation. Someone has to look at it, right? Someone has to take action on it. So that's the updater's job. Based on the update policy that you have set, it can kill the pod so that a new pod gets scheduled with the right resources, right? So yeah, based on the update policy, it can kill the pod as well. That's where the admission controller comes in. So what it does is, after you kill a pod, a new pod would try to get scheduled. But what admission controller will do is, it will intercept that request. It will look at if it kind of closely matches the recommender's recommendation. If it does not, it will update it and let it go through so that it gets scheduled. The scheduling process, as we discussed in the scheduler section, it is like basically picking a node, deciding a node, and then the kubelet will create the pod, right? So this is the flow. So we saw what metric server was. Your container will send or your container's metrics will be available at metric server. Then the recommender will look at it. After looking at it, it will come up with the recommendation. So what updater will do is, it will see if the container's current metric closely matches. So it won't do an exact match. It would do a similar match or near match. I will talk about what near would mean here. But yeah, it would try to match it. If it's within range, it won't touch anything. If it's different, then based on the policy that you have set, it will either kill it. So taking the example that, let's say you have set it to kill the pod, right? That's where we saw that the admission controller will come in, set it with the right values, and let it go through. And after a pod gets scheduled, the containers again metric would start showing up in the metric server, and this cycle would repeat, right? Now let's understand the VPA algorithm. This is like what recommender does. So what it does, it first aggregates metric, right? So for aggregating metrics, it looks at the historical metrics as well as the current metrics. Now for storing the historical metrics, it creates a different resource within KEDA, but you can even configure the recommender to look at the Prometheus server. So you can connect your recommender or the VPA to look at the Prometheus metric instead of storing it itself. But yeah, by default, it creates its own resource. We will be looking at it in the demo. But yeah, it just aggregates historical and current metric. Then it creates a histogram, right? So histogram, most of you, I believe, would know it's like just a plot of the graph. So after calculating the histogram, it calculates something called a target value. So target value is basically the recommendation that it would want, right? So for that, it calculates the 90th percentile of that histogram. The next is, it adds a safety margin. So this is just for like keeping some buffer. So by default, this is 15%. You can configure it while setting up your VPA. The next thing it does is, it does some adjustment, right? So by adjustment, while configuring or creating a VPA, you can set a min and max allowed threshold. So what it will do is, it will come up with the target value. It will then try to see if it comes within the min and max boundary. If it does not, it will tweak it to match it, right? So if your, let's say, target is less than the min, then it would take the target to be min allowed limit, right? So these are like some things that you can tweak. So yeah, that's about the adjustment. Yeah, now let's look at, I have taken the screenshots of the VPA config. So first thing is the kind, right? So kind is vertical pod autoscaler. So it's a CRD or custom resource definition. So Kubernetes allow you to create your own kind of different types, and for that CRDs are used. So yeah, the kind here is VPA. The next thing is the target. So here by target we mean on what resource or on what deployment our VPA is working on, right? So we are saying that our VPA has a name of foo app VPA, which is in the metadata field. It is working on a target or deployment that has the name of foo app, right? So we want our VPA to work on that. The next thing is the update policy, which I just talked about, which is we have set it to recreate. Recreate here basically means if the recommendations or the container's current resource doesn't match the recommendation, just kill it, right? Yeah, the other thing is you can set the what all containers to look at. So this I think is self-explanatory. This is the min and max allowed threshold. Now if you look at the bottom here, the control resources part, we have set it to look at both CPU and memory to come up with the recommendation. That's why we have set the min and max for both CPU and memory, right? So yeah, this is all about the config that you have set. Now let's look at what the recommendation generated, right? So the first thing, so if you look at the recommendation section, in that it says container recommendation. So what container it picked? Foo app, right? So our container was named foo app. In the config we had given star, but it was intelligent enough to pick that up and give us its name. Now, yeah, this is the interesting part. So this is about the near part or the what updater does, right? So what updater will do is so recommendation has lower bound, target. Okay, I will be talking about uncapped target later. So it has lower bound, upper bound and target, these three things, right? So what updater will do is it will look at the pod's current metric. If it lies between lower bound and upper bound, it doesn't have to do anything, right? But if it's beyond that, it will kill that pod, and that's where the new pod will get scheduled with the target value, right? Now, what's this thing as? So there's you might see as uncapped target, right? So uncapped target is basically your target that was before you did the adjustment, which is the adjustment that you did for max and min, right? So VPA doesn't act on uncapped target. It is just to let the configurer know that what does the actual target would look like without your min and max thresholds, right? Yeah, so that was all about VPA. So we looked at what VPA did. It did not it increased the CPU and memory or whatever resources that you have configured vertically. It tried to either increase or decrease it based on the usage. Now let's look at the another type of autoscaler, which is horizontal pod autoscaler. So now you might be intuitively guessing what horizontal here means, right? Instead of increasing the CPU and resources, it will increase the number of pods itself, right? So yeah, so how this is the diagram how HPA works. So HPA works on top of your deployment. So what it does, it tries to we would know that in deployment you can set the replicas field, right? So what it does, it based on some internal calculation, it will try to either increase or decrease the number of replicas, and that would basically lead to increase in the number of pods or decrease, right? Yeah, so this is what a HPA config would look like. I have removed the part where the kind was horizontal pod autoscaler. It was similar to VPA. Yeah, again, if you see the target, we have defined as a simple application called PHP Apache. It's of deployment type. There's a min max threshold, right? So again, most of the autoscalers would provide you some lower and upper bound because you don't want it to go freehand, right? You want some control on top of it. So that's why HPA has a min and max, right? Yeah, next thing is what does it look at to come up with the to come up with the number of how many replicas should be, right? So it for now we have set it that it should look at a resource metric. We are saying that look at the CPU resource, and we are saying that the average utilization should be 50. Now it again can't match exact 50% because it won't exactly match anytime, but it would try to bring it close to 50% average. Yeah. So this is again the diagram of how HPA would work. You would have the metrics of the container pods in your metric server. Then HPA would look at that, come up with the recommendation, and come up with the value, and then it would adjust it in the deployment. Right. Now, what's the formula? Like we had learned what HPA did. Now this is the magic formula that HPA would use. So the formula is quite simple. It's basically the ratio of the current by the desired metric, and you product it with the current number of replicas, and you take the seal. So you can only look at the ratio bit, which is the current by desired. So suppose your current metric is 25, whereas your desired is 50, right? So ratio would come out to be half, right? So it would half the number of replicas that it currently has, right? So in that way, the utilization should now go up, right? Because your resource, the number of pods are underutilized if you have that many. So that's why it is reducing it, and the opposite can also happen.
Cool. So we have looked at HPA, VPA, and Cluster Autoscaler. These are three types of autoscalers. Let's look at the final one, which is event-driven autoscaling. Now, to explain why we would even need event-driven autoscaling, let's again take a look at an example. So if we were to derive an analogy of what the HPA does, with this example where you have a barista, if you don't know, is just a person who makes coffee in a coffee shop, and you have a manager. If we were to draw an analogy what HPA does, if the barista is overworked, if he's tired, if he's stressed out, the manager would simply add a new barista to keep up with the requirements of making coffee. This is what the HPA does. It looks at the barista, it looks at the CPU and memory, and after it goes beyond the threshold, it decides to add a new barista. Now, wouldn't it be better to preemptively assume a new increase in the number of coffees and add a barista preemptively? Well, this is what KEDA does. If you have a barista and a manager, and if you keep on getting new customers, your manager now, instead of looking at the barista and seeing how stressed out he is, he would instead keep track of the number of customers there are. For example, in this case, we are saying that the manager is looking at the number of customer as a metric. So there are 1 customer, 2 customer, and 3 customers. And he says that per barista, I want only 3 customers. So preemptively, once we get 3 customers for the first barista, he adds a new barista to meet the demand of more coffees. So this is what KEDA does. It allows you to scale based on events, based on a metric. So yeah, it scales based on real-time event traffic. It goes beyond just scaling based on CPU and memory. It works with deployments as well as jobs. Now HPA by default, it only works on deployments and stateful sets. But with KEDA, you can also scale cron jobs and jobs. Unlike HPA, it can also scale down to 0. That means you can effectively set a serverless type environment in your Kubernetes cluster, where you would scale down to 0 normally. And when you get some traffic, when you get some event, that is when you trigger scale up. KEDA has a broad integration with 70 plus external systems. So it actually connects to your external systems such as Kafka or AWS SQS to fetch some metric and then scale based on that. And the way you use KEDA is you define your CRDs. These are again custom resource definitions, as Amit mentioned. So KEDA has 2 CRDs defined. This is the scaled object and the scaled job. So whenever you want to use KEDA, you would define your own scaled object, your own scaled job. And it basically tells KEDA which event source to look at and how to scale. Let's now look at the components that are involved in KEDA. It has 3 major components. The first is a scaler. It is nothing but the sensors of KEDA. It connects to your external system, for example, Kafka, and it fetches metrics such as what's the lag maybe on a consumer group. And each scaler specializes on a particular source. So you would have a scaler for Kafka and you would have another scaler for example for AWS SQS. So this is nothing but the sensor. It connects to your external source and fetches some metric value. Then you have the controller, which is the brain. It watches over the scaled object or scaled jobs that you have created, and it decides when and how to scale. So whenever you want to scale, you would define a scaled object. The controller, the brain, it will internally create a HPA. So KEDA internally uses HPA itself. So whatever Amit mentioned, it still applies here. The magic formula, the same formula is used by KEDA. And you have the third component, which is the metrics adapter. Now, whenever your scaler connects to your external source and gets some metric value, Kubernetes or the HPA, it cannot understand that metric value by itself. And for that, it uses this translator. It converts that metric value into a format that the HPA can understand. So these are the three components that are involved with KEDA. And you would define scaled object something like this. In this case, we have defined a scaled object. As we can see, it's a CRD. That's why the kind is scaled object. We are saying to target a deployment that has the name as consumer service. We are saying poll the external source every 1 second. We have a cooldown period. This is telling KEDA that whenever you don't get anything from the external source, wait for around 30 seconds before scaling down. So this is the cooldown period. Again, we have a range, min and max. All autoscalers have this. And this is again to prevent scaling to infinity. And finally, you have triggers. These are actually the way you tell KEDA what external source to connect to. So here we have a trigger for Kafka. And we are saying that monitor the topic that has the name messages. You are giving it a list of brokers to connect to. You are saying that for this particular consumer group called as test sample, I want the lag to be around 500. So then your scaler for KEDA, it will actually connect to Kafka and it will make a metric out of this. So whenever you create a scaled object for this consumer service, you would create it by some kubectl command, and the API server will register this scaled object. And once it registers it, the KEDA, it has a component for an admission webhook. Basically, KEDA's webhook is called. It looks at the fields that you have defined in scaled object and validates them whether or not they are correct. It also does some other validation, such as you can only have one scaled object for a particular deployment. You can't have more than one. So it does such validations. Once it has validated that scaled object, it accepts that the controller, again the brain, it uses scalars in memory to connect to your external source. So in this case, once you define your scaled object, your controller will in memory run a scalar, which will connect to your Kafka. It will get the metric value for this consumer group called test sample for the topic messages. And once it gets this metric value, again it uses the translator to convert it into a format that the HPA can understand. And the controller, again, it's the brain, so it also creates the HPA for your scaled object. So it will create the HPA and it will translate that metric and provide it to the HPA. And the end result is your workload is now scaling based on an external source. Here it's scaling based on Kafka. So that's how you would use KEDA for event-driven autoscaling. Now, usually you wouldn't just use one autoscaler. You would likely combine the autoscalers together. And let's see how that works. So you have KEDA. It will monitor your external source such as Kafka. It will fetch some metric value. And suppose in this case, it determines that maybe we have set the lag to 500. That means at a time we want 500 messages as the lag threshold. If it goes above 500, maybe due to some spike, KEDA decides that the number of pods need to increase. So here the pods are now increased. And suppose the scheduler, the sweaty gamer, it will try to take the pods, it will put it into existing nodes on the cluster. But if the pods, for example, the nodes capacity is full, the pods will be in a pending state. It will be unschedulable. So your cluster autoscaler will kicking. It will try to add a new node to fit that pod onto, and the end result is that you have a new node in your cluster and the pod is scheduled onto that new node. This is when the traffic increases. Similarly, when the traffic eventually dies down, maybe now the lag value is below 500, it's maybe 100. Your KEDA again kicks in. It will scale down the number of pods, and if cluster autoscaler, if it finds out that any node is underutilized because now the number of pods are less, it will eventually evict the pods from that node, and those pods will be scheduled onto existing nodes. And in the end, it will send a terminate node request to your cloud provider. So essentially, when your traffic increased, your pods increase, which increase the number of nodes, and eventually when the traffic died down, your number of pods decreased, and even the number of nodes decrease in your cluster. So finally, in the example we mentioned at the start, you can sleep peacefully whenever there is more demand.
So we will be demoing some of these autoscalers that we just saw. We won't be demoing the cluster autoscaler since we are demoing this on our local, and that would require integration with the cloud provider, but rest of them we can see. So let's start with the VPA. So okay, before starting on that, we have created a Git repository on GitHub. It's public. You can we have uploaded all the files that we will be demonstrating here, so you can even play around and set it up yourself. I will just quickly go through the README just just for you guys so that it is easier to set up. Yeah, so we are running this demo on Rancher. Whatever version, I think any of the latest version should be fine. And we are using a tool called Hey to simulate the load on our application. I hope this is visible, right? The text is visible? Okay. Okay. Yeah, so rest of the things, okay, it's kind of self-explanatory. You would have to set up KEDA and VPA since it doesn't come automatically as part of the cluster. Only HPA is kind of already there as part of the cluster, right? So you would have to set it up. I think there are not a lot of steps for each. Yeah. Cool. So we have also added a simple application. So it's our foo app application. So we have created few endpoints. So this liveness and readiness is required by KTest. I won't go into detail here, but yeah, for our application, there's this endpoint called foo, and to simulate some processing on it, we have added a timeout of sleep of 200 milliseconds, and then it returns back a response, right? So yeah, okay, let's start. I will quickly show. So we are using a CLI tool called K9s to basically see what all is running on our cluster. You can use any other KTest client as well to visualize this. This is just a visualization tool. Yeah, so we have some of the deployments, and our app isn't still running. So let me just quickly run that. Yeah, so I'm applying this VPA. Okay, let's look at what are we creating as part of the VPA. So yeah, at the start you can see we are creating a simple deployment called ping pong app. This is internally using the same application that we just saw. I think these are all not self-explanatory. We are creating a service so that we can route requests to our application. And this is the VPA config, right? So this is similar to what we saw in the slides. Again, the kind is vertical pod autoscaler. We have name and we have given it the target of our ping pong app, right? And we are monitoring for both CPU and memory. So yeah, let's apply this. Sorry. Yeah, so as you can see, we have created a deployment, a service, and VPA. I hope this is still visible, right? Okay. Yeah, so now let's go back to our cluster. So as you can see, the pod is starting up. The pods are starting up. So we have set the replicas to be 2. So 2 pods will be there. We saw it also created something called VPA. So VPA, as you can see, it is showing few things, right? So it is saying that the current recommendation for CPU is 63 millicores and some memory, and this is the update policy, right? And the name we saw earlier was ping pong app VPA. So before applying or simulating some load on it, let's look at the request for our pod. So as you can see here, currently the our application or the pod is also has a request of 63 millicores. So let's now simulate some load on it, and let's see what happens here. So yeah. So I'll quickly copy the command to simulate load on it. So as I just said, like earlier, we are using a tool called Hey. So yeah, so let's look at the anatomy of this. Like we are using this tool. We are saying that we want for the load to be simulated for, let's say, 200 seconds, and we want number of concurrent requests to be 1000. Since I want to put huge load on it, I have given it quite a bit. But yeah, and this is the endpoint that we will be hitting. So before doing this, let's just do a simple curl and see what response we are getting. Okay, I haven't port forwarded it. Let me port forward it. So okay, let me show that as well. So let's port forward to both the pods since we want to simulate load on both. So I am port forwarding first one to 8000 and the second one to 8001. Yeah. So as you can now see, we are getting back a simple response called bar. Now we can start simulating load. I am creating 2 commands, one for each pod. Yeah. So yeah, the load has started for the first and this is for the second, right? Now let's look at what's happening in the pod. As you can see, we are getting logs for the requests that we are making, and quite a lot. So this would mean the CPU getting increased. And now let's look at what VPA is doing. Okay, it is still, okay, the load is not enough yet. It is still, yeah, okay, I think the VPA worked. Yeah, as you can now see, it has increased the CPU to now 163 millicores, which basically meant our updater would have cleaned up the pods or terminated the pods sequentially. And now if we look at the request, you can see the CPU has now increased to 163 millicores, right? So this is what the recommendation or recommender recommended. And yeah. And okay, another thing is, as you saw, the number of pods still stayed the same, 2 pods only, right? It's just the resources that increased. So that's what we saw, that like what VPA does, kind of. So this was all about VPA. Let's look at HPA. Yeah. Okay, I will stop putting the load now on it, and let me clean up as well. Yeah, so I have just deleted our application for our VPA as well. Now let's look at the HPA config. Yeah. So again, we are creating a deployment. We are calling it FizzApp. We are setting services, and this is the HPA config. So here the kind is Horizontal Pod Autoscaler. We have given it some name. Okay, I won't go into detail here, but this is basically we are controlling how often HPA should get triggered, basically. But yeah, the rest of the things we can still take a look at. The first one is again the target. We are targeting the deployment that we are creating above. We have set min and max to be 1 and 20, and we are looking for the metric or average utilization to be around 50%, right? So yeah, I think same fashion we have to apply this HPA. Yeah, so I hope this is visible. Deployment, okay, we created again deployment, service, and something called HPA, right? Now let's look at what the HPA is doing currently. So as you can see, it is showing some CPU, since we have set the CPU to be the target metric. Currently, this 50 is the target value that we are saying we want, and this is the value that it is currently reading. Since we have just created our pods, it is unknown. Give it a couple of seconds, it would be able to now get the live metric. So we can check if our application is up. So we created this Fizz app. We have set number of replicas to be 1 only. Okay. Okay, till then, okay, it came up. So now it is showing it to be 7%. So current is like 7%. Now in this case, what should happen, right? You might think that it should scale it down more, but as we saw, we have set the min replicas to be 1. It won't do that, even though the current utilization is a lot less than the average one that we have set. So we will do it the other way around. We will simulate some load and let's see what it does now. So for doing that, again, we can use the same utility. I will exit this. We don't need this. Yeah. So yeah, let's okay, maybe put 500 concurrent requests. We are putting it again for 200 seconds, right? Okay, before doing that, I need to port forward. Okay, we have port forwarded. Now we can simulate. Yeah, so we have started the load simulation. Now let's look at what's happening. Again, we are seeing logs for the API hits. Now we can observe this CPU. So this CPU should now spike up since we are putting a lot of load on it. Yeah, and based on that, it should increase the number of replicas. Yeah, so something is happening. It is now maybe querying for the metric again. Okay, I think load is still there. Okay, till then we can maybe look at the config only. Yeah, so this is okay. We saw earlier what we had like the min and max. There are name, and we are targeting for this our deployment Fizz app. This is the like the ratio that we are seeing. Currently the target would be 20, and the current it is okay, still not able to fetch. Okay, I think we have to look at the reason. Okay, live debugging. Yeah, okay, so we have put too much load on it. I think due to that the pod went into the unready state. So we saw this, right? There's a readiness API that we are hitting, due to which, okay, so let me just reduce the load on it and then we can observe again. Okay, now let's put less. I think maybe 200. Okay, yeah. Yeah, so again we are simulating some load. Again we are seeing API hits. Hopefully now it is able to query the metric. And this is why we need the readiness and liveness, right? If your pod has too much load, it might not be able to satisfy the API request. In that case, if the readiness fails, Kubernetes will route those requests to the other pods which are in the ready state, right? So you don't have downtime. Yeah. Okay, yeah. Now you can see the CPU is currently at 115%. We have the target of 50. So the ratio comes out to be like more than 2, I believe. So it should scale up to maybe 2 replicas, right? Okay, it did 3. I think it took a seal. Yeah, so now we can see it created 2 new pods. And if you look at the resource or the request, it would be same across all of this. So this is in contrast to the VPA, where we had increased it rather than increasing the number of replicas. So yeah, it increased. Now we can even try scaling it down. So I will stop putting load on it, and then it should reduce the number of replicas automatically. Okay, it will take a couple of seconds, but till then we can see the events, right? So if you look at the events, it says successful rescale, and it says the new size should be 3, and the reason for that is the CPU resource utilization is above the target value, right? So as you can see, the CPU current utilization has dropped to 7%. So this would mean reducing the number of replicas. Now if we go back to our app, it has increased to now 1 pod, right? So yeah, this is about HPA. Okay, let me just clean up this as well, HPA as well, sorry. Cool.
Cool. We have looked at HPA and VPA. We can now look at KEDA, which will be driven by events. In this case, we will be driving it through HTTP event. Now, what does an HTTP event even mean? You can either expose a HTTP event using something like Prometheus. You can have Prometheus scrape a metric for HTTP request rate and then scale based on that. But KEDA also has a HTTP add-on, which will actually calculate what a request rate is for you and expose it as a metric. So before even going there, I would like to show you what happens when you install KEDA. As you can see, you can ignore the add-on for now. You have these 3 components. We talked about the 3 main components of KEDA. You have admission webhook. We said that it will validate your scaled object. We have the operator, which is your brain, and we have the metrics API server, which is your translator. Now, similar to what Amit did, we will be using the same app. So I'll just quickly deploy that application. So here we have separated it into 3 files, but it's the same deployments. Here we are saying it should have 2 replicas. We have a service for it, and we also have a scaled object. Now, before going into that, let's just quickly apply it. And before going into the details of what we have configured the scaled object to be, I would like to simulate some load to explain what happens in the first example that we have given, where you have deployed your application and you have no autoscaling enabled on it. Let me just quickly simulate some load. Before that, I'll port forward. Cool. So now we have simulated some load on your application, and currently we have port forwarded to a single pod. That means KEDA is not kicked in. It's not currently autoscaling. And this is the same scenario where you have an application deployed and you have no autoscaling setup. Now, while that load is ongoing and that pod is fighting for its life, we can quickly look at what the scaled object we have configured. So, firstly, this is an HTTP scaled object. If you go back to the talk, we haven't defined what it is. This is because this is not part of KEDA built in. It's an add-on that KEDA supports, and its job is to essentially create a metric for HTTP request rate. As mentioned, you can also use Prometheus for this. So in this case, we have in the annotation firstly said, do not create a scaled object for us. We'll create our own scaled object. There may be multiple reasons to do this. One reason can be you can define a scaled object with actually many triggers. So in which case you would define your own scaled object. In the specification, we are saying whatever requests that come from this host, keep track of a metric for it. We are saying if a request comes from any of this host, route those requests to this endpoint. So the way this add-on works is it deploys a pod that is a proxy, and you actually send your request to this proxy pod, and the proxy pod will divert your request to your end deployment. So here we are saying whatever requests come to this proxy pod, if it has the foo.local as the host, divert it to this deployment, which is our foo app as we mentioned. And for actually calculating the metric, we are saying you need to calculate the request rate, which is the number of requests per second. Granularity here is nothing but how often you want to calculate this metric. So here we are saying every second you calculate the request rate. Target value is the desired target. We are saying we want the request rate to be roughly 5 requests per second. If it goes beyond that, scale it up. If not, scale it down. And window here we are saying basically the duration for which this request rate is calculated. So here it's 5 seconds, meaning what's the request rate, the average request rate within the last 5 seconds. So this is nothing but to calculate the metric value using the add-on. And now let's go back to the scaled object which we have looked at. So in the specification, in the advanced properties, this is a great example of what you should not do in production systems. Here we have configured it. Basically this configuration is telling us that whenever you want to scale, do it very fast, and this is just for the demo part. You wouldn't actually want to do this in production systems. So just to give a brief overview, for the HPA config, we have given the behavior. While scaling down, there is a property called as stabilization window seconds. This is defaulted to 5 minutes, and it basically tells HPA that if you want to scale down in this case, don't do it that frequently. Within the given stabilization window seconds, use it to slowly scale down or scale up. And here we are setting a policy that says if you want to scale down, you can do so by 100%, and you can even scale up or down in 1 second. So this is what you shouldn't do. Ideally, you would set this to a very high value because you want to scale up and scale down slowly. This is to prevent something called as flapping, in which you would scale down and scale up infinitely. And yeah, usually you would have this at a very high value. Now coming back to the scaled object config, we have the cooldown period. We are saying don't do any cooldowns. We have set the min and max to 1 and 10. We are saying that you should poll for this metric every second, and we are targeting this deployment. And as we mentioned, we are using an add-on for actually calculating the metric. So in the triggers, we have used a scaler of type external push. If you are scaling based on some other external source, you would maybe put in Kafka here, or maybe AWS SQS as well. And in the metadata, we are saying you would get this metric from this add-on. That's basically it. So now let's look at the pod that was fighting for its life. And if you see, we queried it for 60 seconds. We queried with 100 concurrent requests. And this is basically limiting the request rate. We are saying at max go at 200 requests per second. And if we see the average response time, it's roughly 1.6 seconds. But if you remember the application which Amit showed, we are just doing a sleep for 200 milliseconds. So that means it's taking a lot of time for the request to be served. And this is the case where we saw in the start where you couldn't anticipate the traffic. Now let's quickly send this request through the proxy, which is configured by the add-on, which will create this metric for us. So in this case, I'm actually port forwarding to this interceptor, which is the proxy for the add-on, and we'll port forward on 8080, which is the port for the proxy. And if you want to see whether or not this proxy actually forwards the request, let's send a simple curl request to this proxy pod. And as we see, we are getting the same response. That means the proxy is routing this request to the actual pod, which is giving you this response. And now let's simulate some load. So here, similar to the previous one, we are just adding a new flag, which is a host, because in the scaled object config, we have given the host as foo.local. So now as the load is being simulated, we can go to the scaled object. And okay, before that, we can also go to HPA. So as you can see, there is a new HPA. We didn't create this by ourselves. This is the HPA that the scaled object created for us, that KEDA created for us. And if we look at the target, here it's no longer scaling based on just CPU and memory. Here it's the request rate, and here we have we have set the request rate target to be 5. The request rate target here comes at to be 5 here. And if we go back to the deployment, we can see now it has scaled up from 1 replicas now to 3, and I guess it will keep on scaling up as we get more requests. And if you want to see what KEDA actually does, we have it exposes a metric, and we can actually query this metric. So this is the current request rate, which is 171, which is way higher than the 5 that we have set, and that's why the number of pods has now increased to 10. But if you see here, the requests have stopped, and the pod should also now scale down by its own. So yeah, if we see on average, the request rate are now at 0.6 seconds. So the request rate have gone down significantly. Yeah, and if we query for the metric, it should no longer give us anything. So you are saying you are not getting any metrics for this particular request rate. Cool. Yeah, that's it for the demo portion. You can go back.
Yeah, so okay, till now we saw a bunch of autoscalers. We have given hints throughout the slides what each one is useful for, but let's quickly recap where each one might be helpful, right? So the first one is the HPA. I think most of the folks who start autoscaling things on Kubernetes would start off with HPA. It's already there as part of the cluster, and this is what you should start out with because it's the most effective, and it applies to a lot of use cases as well, right? Now the next is the VPA, so HPA has another thing. If you have a stateless application, it might be a simple web server or some Kafka service or all of these things. Not Kafka, normal stateless web server, those things you can use HPA. But if you have some stateful application, you might want to vertically scale up those resources. So for that, VPA would be helpful. And suppose now, and one disclaimer with VPA is not good for spiking load, right? If you have very short spikes, VPA is not good at that because it does historical aggregation as well, and it won't be able to quickly get that metric, quickly scale up and then scale down. For the demo, I kind of set the threshold very aggressive. That's why for the demo it took less time, but VPA won't be ideal for very short spike loads, right? For that you can use the other autoscaler, which is KEDA. And KEDA is also applicable for custom metrics, right? It can be your Kafka lag, or as Vighnesh showed, it might be your HTTP traffic. In all of these cases, KEDA would be useful. And to support all three autoscalers, you would need a cluster autoscaler, because since you are dynamically scaling up and down, your node should reflect that, right? Because if you have a bunch of nodes that aren't needed, you are paying for that. And if you need more, you should dynamically provision that node rather than keeping a lot of nodes as a backup bandwidth, right? So yeah, that's about what each autoscaler should be used for. Yeah.
We can move on to the takeaways. So firstly, you should have warm nodes. You should have nodes that are there that don't have any capacity allocated to your actual application pods. This gives you some time for actually the cluster autoscaler to go and communicate with the cloud provider, to run simulations, and basically ensure that when it wants to add a new node, your applications that are important to you, they are not facing any downtime. The second thing is that you always want to avoid flapping. This is the rapid scale in, scale out that happens up to infinity. And you want to avoid this for a bunch of reasons. You are wasting CPU, you are wasting memory, you are wasting resources of your autoscalers as well. And to avoid flapping, you would need to configure your thresholds wisely. You need to use cooldown periods. Don't do what we did in the demo. You need to tune your thresholds. You need to always keep on tuning them. You need to add some sort of monitoring to actually avoid scaling up and scaling down very frequently. And usually people add buffer to your resource requests whenever you create a deployment. So if your app on average is using, suppose, 100 millicores of CPU, you would add some buffer of maybe 115 or 150 to actually keep up with the load. And the next thing is that you should always configure liveness and readiness probes. These are proper probes that Kubernetes uses to query your pod and basically get two things out of it. Firstly, whether or not it is healthy, which is the liveness probe. And if the pod is no longer healthy, your Kubernetes will actually kill that pod and spin up a new pod to serve the requests. Secondly, you should have readiness probes configured. Your readiness probes tells Kubernetes whether or not it should divert traffic to your particular pod. So if you don't have this configured and autoscaling is triggered, you might have pods that come up based on some metric, but they won't be ready to actually serve the request. That means in the end, the customers will still get errors, 500s and 404s, so on. So you should always configure these two. Next, the autoscalers, they usually work best together. Combining HPA with Cluster Autoscaler is a very common practice and it's very effective as well. But you wouldn't want to plug and play autoscalers as is. For example, if you use VPA with HPA for the same deployment, you might see a scenario where your VPA will actually try to increase the memory and CPU for your pod based on demand. And then HPA will take this as a decrease in the actual utilization. So your VPA tries to add a new pod with higher CPU and higher memory, but your HPA will then try to scale down because the utilization has fallen below. So you wouldn't want to plug and play these randomly. KEDA can replace or even complement HPA. So you can set it up such that HPA scales based on CPU and memory, but KEDA scales based on some other events that you have. And autoscaling, it's not set and forget. You need to set up monitoring. There are Prometheus metrics that KEDA itself exposes, as well as Grafana charts already there for KEDA, Cluster Autoscaler, HPA and VPA. So you should always set up monitoring and then fine tune the thresholds that we mentioned to avoid flapping. And finally, scaling strategies, they impact cost, they impact reliability. If you have the right autoscaling configuration setup, it means you would have better performance as well as reduced costs. But if you have the wrong autoscaling setup, you might encounter situations where you have over provisioned. For example, if you have HPA setup with a very high threshold, maybe or very low threshold, suppose you have it at 20%, it will always keep on scaling up. That means you would have over provisioned where it's not needed. Or if you have it set to a very high threshold, suppose 80 or 90%, it will lead to OM kills and latency spikes where even before scaling up, your application has died down. So you should always keep on monitoring and tuning your thresholds for all of the autoscalers that you use. So these are the references we have used. The first one is the GitHub repository where we have set up all of the code for the demo, and the rest are for our slides. Cool. We are now taking questions. GitHub, yeah.
Go through KEDA and then it goes to the actual application, the events and testing. So that's why the configuration, then you configure that the request should go to KEDA and then you target a particular deployment and do that.
Yeah. Okay. So the question was the request. Do we need to always configure it through KEDA? Does it go through KEDA before actually being scaling up or scaling down? Is it? Okay, for this case, we are using a HTTP add-on, and for that, to actually calculate the metric, it requires it to send a request to the proxy. But in the usual sense, you can also set it up based on Prometheus metrics. So your application itself can expose a metric for what's the request rate currently, and you can configure it to scale based on that. For this demo, we just chose the HTTP add-on since it was simple to set up. But yeah, it need not go through that proxy.
Which is being exposed on Prometheus or anywhere else, it will look at those metrics and according to that, KEDA will take decisions and request may not.
Yes, correct.
You might repeating that question statement so that it gets recorded.
Yeah. So what he said was basically you would configure this on your application whenever you are not using the HTTP add-on, and your application, your KEDA will then poll the metric and then it will scale that application. So it need not go through the proxy. Yeah. We'll post this on Meta. Yeah. Go ahead.
Steps will again, like initial containers and all those will run again and then it will start. There will be a downtime.
Yeah. So, okay, basically the question is, since for VPA, the updater can kill the pod so that a new pod gets scheduled with the updated resources. All the steps, basically the pod is getting started up again. It's kind of an entirely new pod, right? So, that will happen. That's for sure. But in the newer KTest version, they have added a capability of resizing the pod's request. So your pod won't go down. It would resize the request. I haven't explored it, but it's there in the newer version. So you can check that out, how it can be done without basically killing the pod even.
One thing which I initiate it, and then when it's it gets started, it is stable and it takes limited resources than what it takes during initialization. So do you have anything which can be done for this particular scenario?
Okay, so the question is sometimes few of the application it takes, okay, I'm rephrasing it, let me know if it's correct. So it takes some time for some of the application to start up, and maybe then it takes time to basically the entire application to start up and start serving traffic, right? Is that the question?
I'm saying that when you start it, it takes a lot of memory, say 500 MB it's taking in the initial startup stage, and once it's cooled down, it's running like the real time. After the initial startup, it only takes 100 MB or 50 MB of RAM. So what can be done in this scenario, like for the startup that is taking a lot of memory and CPU resources?
Okay, so from scaling point of view, it's a one-time activity, right? So once it starts up, it doesn't take that much. So you can configure if you want auto scaling, it won't affect that because it generally, like in VPS case, it does a average and historical metrics, right? So
in VPS, it will restart, right? So again, it doesn't make any.
yeah. So okay, so you can.
100 MB of memory, and then further if you want some up in 150 MB or so. But just for startup phase of that container, it takes 500 MB. So is there anything which can be done for this particular scenario? Because VPHP and all those things won't work in this.
Yeah, okay. So there are configurations in your autoscalers that you can use, for example, initial cooldown period, which is the period for which it won't actually fetch that metric value or calculate that metric value. For example, in KEDA, scaled object, you can give an initial cooldown period for which it will not actually calculate the metric value. And till that time, your application will take time to start up. And you should also update the polling interval so that the metric value it changes over a longer duration of time. So you can set it to maybe 30 minutes or 45 minutes so that your application will get ample amount of time to start up. And most of the metrics that we saw, they are averages, so they are computed over a duration of time. So even if at the start it takes a lot of CPU and memory, over time the average should pan out, and yeah. So you can configure the initial cooldown period, the polling interval, as well as this config.
Yeah, okay. I think basically you can as Vighnesh said, you can increase the polling for the demo. Since I wanted it to do things rapidly, I had yeah.
Might come in during real applications.
Yeah, in that case, I think the polling interval should help. You can configure it to maybe not poll almost every second. You can add that delay so that after the container starts up initially, then it can poll, and then it would get the normal utilization metric that, and based on that, it will scale. Yeah.
But we have resources, limits, and requests as well. So, what is the real requirement of PTA if we have set resources, limits, and a higher value for requirement? So, PTA is there. Okay, we can set a limit of request limit of let's say 1 CPU maximum, and PTA also does almost the same thing. So, what is the real difference between these two?
Okay, so even if you take that into account, let's say you give it too less of a request, but you set the limit to be too large because you want that buffer thing, right? But it can, okay, first of all, then you are saying your pod can take up that much of resources. And from KTES point of view, it has to manage that, right? So when a node gets evicted, it looks at which all pods need to be killed first, right? So in that sense, the pod which does not state its requirement like very close to the target, if there's too much difference, your K-test will think of it as it's not a good citizen because it is claiming a lot more than what it is required, and in that case it will kill that pod first. So that's why we have something called pod disruption budget and those things, right? And basically want those limits to be even close to what you really want, right? Because it can happen that you set the request too low, but on average it's taking more always, right? So starting it up with the less resource means you have to wait for that. It might take more time for the container to even start up, because it has to, let's say it generally requires 20 millicores, you have set it to be 20, right? So from 20 to 50 it will have to wait, right? So that more memory it gets from kubelet, and then it will start running. So in that case it's better. Yeah, you are right. There's still the need of resource and limit, but you should not take it as a free hand to do everything, right? Yeah, in combination, okay, I didn't show it, but in combination to request, it also sets the limit, because your request can be more than your initial limit that you have set, right? So in that case, it has to set the limits as well according to that.
Limited resource environment, right? What if the resource limit is exceeded? Then will it auto scale, or it should not the person, or what will it be?
In VPA's case, if it has those metrics and it has some past context about it, it won't hit that limit, because it will know that for this pod generally it takes more than this, more than the limit that you have set. So it will expand it or increase it beforehand. So it won't happen. But yeah, in case yeah, then it will be a OM kill, and a new pod would have to get scheduled. You can't do much there. So let's say for the example of it's a very spiking load, right? Suddenly your website gets very popular in a day, and suddenly you get a huge traffic, right? Now for the past few days, your VPA won't know, right? Because it hasn't seen that much traffic. So for the initial case, it would be might get OM killed, but for and if this keeps on happening, if your website is still popular for like some time, it would take that into account and set the limit to be more than what's even at the spiking load, right? So then there it would help, but for the initial case it won't help that much. So that's where you need to, sorry? Yeah, it would work. So that's where you should have other scalings in place, where like KEDA, since you can get a lot more customers, lot more traffic. So there it would fill. That's why we said it's not like one autoscaler would fit every use case. They have different use cases, and that's why you can even use it in combination, right? Yeah, so I have attached. Yeah, sorry. So the question is, what all different other? So in the screenshot and in the demo, we have set the update policy for VPA to be recreate. The question is, are there any other policies that you can set, and what are those, right? So there are other policies as well. I think one is basically off, which basically means your updater won't do anything. Your recommender will come up with the recommendation. You have to manually set those limits in your deployment. Updater won't do anything. I think there are others as well. There's one called auto, which auto internally basically means recreate. So by default, VPA would always try to kill the pod if it doesn't matches the ranges. Yeah. Yeah, okay. So that's one thing I didn't go through. So the question, sorry, my bad. So Yeah, okay. So the question is, VPA has a concept of a confidence interval, and how does it work, and where is it getting stored, right? That's the question. So basically, okay, well, let's first understand what confidence interval is, so that the rest of the folks would also know. So the confidence interval basically is like how, since you are coming up with the recommendation, right? You have to be, confidence interval basically means, or it's not called confidence interval, it's called confidence multiplier, which basically means how confident are you in your recommendation, right? So let's say I set up my VPA today only. Now it comes up with some recommendation, it tries to apply those things, but does it have that historical information, right? It doesn't have that much, right? So I'm not that confident in my recommendation. So that's where the confidence multiplier comes in, where as and when it gets more and more historical metrics and it sees more, its confidence in that recommendation would increase. That's why you multiply it with the confidence multiplier, which basically it's like a number only. You multiply your target with some ratio, so that the recommendation gets tweaked to that. Now to the point where does all these things get stored, right? So the confidence multiplier gets stored along with the historical metrics, right? Because recommender has to get the historical metrics. Now it can't query the metric server every time for last 30 days, last 60 days, right? So what it does is it creates a checkpoint. So there's a resource called VPA checkpoint, which basically means it aggregates the historical metrics into a histogram, and that has the confidence multiplier. So the next time it runs, it looks at whether I have some checkpoint in place. If it's there, well and good, I will get that, combine it with my current current metric, and then come up with my recommendation. If it's not, then it will look at whatever is available from metric server, whatever last few days it will do. So in that way, confidence multiplier helps whether are you sure in your recommendation or not.
We are getting the data from the HTTP. So what exactly the formula we are calculating?
Okay, I don't know the exact formula, but the general sense is, as and when the time passes, it will try to reduce the lower bound and upper bound to be as close as possible to the target, and it would try to merge, or basically bring the lower bound as close to the target as possible, faster than it would do for the upper bound, right? Because giving a pod more resources or a container more resources is good enough than giving it less, right? So that's why it tries to converge the lower bound and upper bound to as close as the target. Yeah, you can take a look at the link I have attached. There you can find the algorithm for that as well. Yeah. You want to take it? Yeah.
So, okay, the question was, we have talked about scaling jobs and what use case would be there to scale a job. For example, so jobs have a field called as parallelism, which control the number of pods it spins up. And suppose you are using KEDA for scaling the jobs. Maybe at some day there is a holiday, and you are doing some batch processing job which processes a lot of data. In that case, you can actually configure the metric value, and based on that, if you have less data to process, because maybe it's a holiday, there is not much data, then it will actually fetch, you can have a metric based on the size of the data, and based on that, if there is less data today, it will run it with less number of pods. But if for a certain day you have a lot of data, it will also scale the number, it will change the parallelism such that you would have more pods running, doing that bad job processing data, and so on. Cool. Any other questions? Cool.
Okay, thank you all. Thanks, Vighnesh, Amit. I'm pretty sure, I think you have taken the efforts to ensure that we don't have sleepless nights. But I think we want to appreciate the effort that you guys have put in.